Next is oxides of nitrogen. That is the next important topic, oxides of nitrogen. So table 7.3 as well as table 7.4 give us a detailed picture regarding the various oxides of nitrogen. Let's go through one by one. First of all, dinitrogen oxide. Dinitrogen oxide, that is nitrogen 1 oxide. Nitrogen 1 oxide means that is the stock notation. Oxidation number is 1. I think all of you know what is this oxide, popular known as laughing gas. Nitrous oxide called a laughing gas. Inhalation of which causes a hysteresis laughing sensation called euphoria. Actually, it is a local anesthetic substance which is which is actually making the sensation of the face muscles are lost. It's used as an anesthetic chemical in dentistry also, right? That is nitrous oxide, laughing gas, which is prepared by heating ammonium nitrate. Ammonium nitrate on heating N2O and water, right? You know, many reactions that we learn in inorganic chemistry, it's not simply need to mug up, but you can apply some logic to memorize how that product is obtained. For example, ammonium nitrate on heating, you are getting nitrous oxide. There can be a complementary reaction related to this. You see that ammonium nitrate upon heating, what actually happens is water molecule is out. How many water molecules? As many hydrogen, accordingly there will be water molecule, 4 hydrogen, no? So 2 water molecules will be eliminated. So 4 hydrogen, that is 2H2O means 4 hydrogen and 2 oxygen out. And what you get is N2O. Remaining is N2O, so you get the product. That's a simple way to memorize rather than simply trying to by heart it. Not apply some logic, because they may be trying to confuse you with another reaction which is ammonium nitrite, NaNO2, ammonium nitrate. Upon heating, again there will be removal of water molecule. How many water molecule? 4 hydrogen, so 2H2O out. So 4 hydrogen and 2 oxygen gone. What remaining is? Very simple, no? You have remaining N2. So N2 gas will be the result. So upon heating ammonium nitrate, nitrous oxide is liberated. While heating ammonium nitrite, N2 gas is liberated. You can easily find out without trying to by heart it. You can apply this kind of logic, not in all reaction, but many reactions. You can apply this kind of logic to find out what will be the product formed in a reaction like that. Try to apply that logic. You will be able to successfully finding the products in many of the reaction applying your own this kind of logic. Okay. Here the logic is very simple. Water molecule is liberated. Water molecule is removed. Because it is a heating process, water is out. How much water is out and what is remaining will give you the product. Let us go through again. That is about nitrous oxide. Next is nitric oxide called nitrogen monoxide. Nitrogen monoxide. Nitrogen 2 oxide, also called nitric oxide. Nitric oxide, right? The most reactive oxide of nitrogen, nitric oxide, having +2 state, obtained by reacting sodium nitrite with ferrous sulfate and sulfuric acid. You are getting NO gas. Sodium nitrite with the ferrous sulfate, it's a redox reaction. You may easily be able to understand, I believe. You see, NaNO2 nitrogen +3 state reduced to +2 state. Ferrous Fe2 plus oxidized to ferric. So ferrous is oxidized to ferric and nitrite is reduced to NO. Now both are colorless gas, nitrous oxide as well as this one. Both are colorless gas and both are neutral also. What is meant by a neutral oxide? Neither acidic nor basic, right? So two important oxides of nitrogen, nitrous oxide and nitric oxide. Nitrogen 1 oxide, nitrogen 2 oxide. Next. Next it is dinitrogen trioxide. Dinitrogen trioxide. That is the next one. Dinitrogen trioxide or nitrogen 3 oxide N2O3. That is a blue colored solid, available as blue colored solid, and it is acidic in nature. As the oxidation number increases, for multiple oxides if it is available, as the oxidation number increases, acidic character increases. That's a general trend. Okay. Now, how do you get N2O3? By treating NO with N2O4, you are getting N2O3. NO reacting with NO2 or rather N2O4, you are getting N2O3. That is N2O3 dinitrogen trioxide. Next is nitrogen dioxide, NO2, nitrogen 4 oxide. Nitrogen dioxide, that is a brown colored gas, acidic in nature. It is having a single electron present in it, and hence it is paramagnetic in nature. It is an odd electron system and it is colored in nature, right? Brown colored gas obtained by heating heavy metal nitrate. You get a brown colored gas along with the liberation of oxygen. Heavy metal nitrate on heating, you get a brown colored NO2 gas along with the liberation of oxygen. This actually we are discussing in case of abnormal characteristics of lithium also. Hope you remember. Lithium nitrate, the one and only nitrate from alkali metal which produces brown colored gas upon heating. Lithium nitrate on heating, we get lithium oxide plus oxygen plus brown colored NO2 gas, while sodium nitrate does not. Sodium nitrate converted to sodium nitrite liberating oxygen, you don't get a NO2 gas. Such differences we are learning in the 11th standard topic itself. That is about nitrogen dioxide. Next one is dinitrogen tetroxide, nitrogen 4 oxide N2O4. N2O4 is basically a dimer of NO2. N2O4 is basically a dimer of NO2. NO2 undergoing dimerization, you get N2O4. So two NO2 molecules joining to form a dimerization, we get a dinitrogen tetroxide N2O4, where that single electron is used up for bonding and hence it turned colorless in nature. The brown colored nature of the gas is disappearing due to the involvement of that single electron in bonding. So it is colorless gas or colorless solid or even in the liquid state, and of course it is acidic in nature. And there exists an equilibrium like this. The brown colored NO2 gas upon cooling, it is converted to colorless N2O4, and colorless N2O4 upon heating, it is converted to brown colored gas. There exists an equilibrium between N2O4 and NO2. NO2 taken, brown colored gas taken in a glass bulb. If you are immersing into an ice bath, gradually that brown color decreases. Now if you take colorless N2O4 in a glass bulb and just try to heat it, you can see the brown color develops. There exists an equilibrium between NO2 and N2O4, right? They are dimers. This is the dimer of this. Next is dinitrogen pentoxide. Dinitrogen pentoxide. That is nitrogen 5 oxide N2O5. That is the most acidic among the list. Most acidic, available as a colorless solid, obtained by reacting nitric acid with the dehydrating agent P4O10. Nitric acid with the P4O10, you get N2O5. I think many of you know this is called anhydride of nitric acid. This is anhydride of nitric acid. This when treated with water, you will be getting nitric acid, HNO3. This is called anhydride of this, while this is called anhydride of nitrous acid. Right? And that is very simple to find out with their oxidation state. plus 5 here and here, plus 5, plus 3 here and here, nitrogen plus 3 state. So an oxide when treated with water, which acid is obtained? That tell us anhydride of which acid, right? And there are mixed anhydrides also which may give multiple characters. For example, NO2 plus 4 state, it can go to that side and this side, mostly to this side because that is stable and this is unstable, prepared in situ. All of you know how to prepare nitrous acid. All of you know by mixing NaNO2 with the dilute acid, you get a nitrous acid and that is prepared in situ, right? These are the important oxides and their name, formula, oxidation number, method of preparation and properties. There is one more important tabulated arrangement available in the textbook, as all of you know, regarding the molecular structure of these oxides. Very, very important. Molecular structure of these oxides, which is also very important. Let's have a look at the table 7.4 regarding the molecular structure of these oxides one by one. First one, nitrous oxide. Have a look at nitrous oxide. How the molecular structure is available. It is a linear molecule. It is a linear molecule. There is N-N bondage. N-N bondage, two resonating structures. You can have a double bond and a triple bond. So what will be the bond order? That was a previous question. What is the bond order in nitrogen-nitrogen? In one structure, there is double bond. In another structure, there is triple bond. So what is the bond order? 2 or 3? It is neither 2 nor 3, but will be the average. So it will be 2.5 will be the bond order. Average. Resonance averages the bond character. Right? So the bond order over nitrogen will be 2.5. Okay? And it is linear in shape with a bond length 113 picometer between nitrogen and 119 picometer with the oxygen. Next is NO, which is a odd electron system. Hope you understand. That is a odd electron system. NO. It is odd electron system, and that already we are learning in the limitation to octet. Limitation to octet, three important category, incomplete octet, odd electron system, expanded octet. A few example we are learning in the odd electron system. One is NO, right? Nitric oxide, highly reactive and immediately it react with the oxygen giving converted to NO2. Next is N2O3. N2O3 is rather planar in shape, and that is the characteristic shape, maintaining NO bond angle 130 degree, while ON bond angle 105 degree. See, this bond length is 121, while this bond length is 114. So there are two different kind of NO bond present. One NO bond is slightly larger in size than the other. This NO bond is shorter. This NO bond is shorter, while this NO bond is bit larger. Okay? And look at the bond angle, will tell you why. Here the bond angle is 117. 117. Here the bond angle is 105. So larger the bond angle, you see ON bond angle. Bond angle is larger. Bond angle is larger. Here the bond angle is slightly shorter, 105. So all this is going to influence the bond. Anyway, there are two different kind of NO bond. One NO bond is slightly shorter, one NO bond is slightly larger, right? While NN bond length is 186 picometer planar. Sir, should we go through meticulously these molecular dimensions? Not like learning the dimension or by heart, but why can't there be a relative question like this? See, this molecule contain two different NO bonds. That can be a question, no? And which is shorter one, which is longer one, that can be come as an indirect application level question. So you have to not to memorize the data, rather it is better you must have a relative picture regarding are there identical bond with the different characters. which is shorter one, which is longer one, which is bond angle shorter, which is bond angle larger. That kind of comparison can come as a question. I don't have to tell you. Now, one another point, a couple of years back, even for IIT Advanced, one question came, integer type question. The number of lone pairs in N2O3, that was a question some 5 years back, I believe. 5 years back, I believe. JEE Advanced question. There was a question, number of lone pairs in N2O3. So you have to go through meticulously on this, right? How many lone pairs? Very simple. As many oxygen into 2 lone pair. So it will be 1, 2, 3, 4, 5, 6, 7, 8 lone pairs are there. There are 8 lone pairs present. As many oxygen into 2, as many nitrogen into 1 will give you simply the number of lone pairs, unless otherwise there is no permanent formal charges. Okay. So that is about N2O3. Next is NO2. I told you NO2 contains a single electron, and that is the reason why it is having some paramagnetic behavior as well as some coloring character. It is also angular in shape with 134-degree angle, 120 picometer. That is bend in shape. That is NO2. And that NO2, when undergo dimerization, the color is lost. That NO2, when undergo dimerization, you can see that single electron is used here for bonding, and therefore it remains diamagnetic and the color is lost and it becomes colorless in nature. This is N2O4 structure. You can evaluate how many lone pairs will be present and so what will be the characteristics. It's once again is planar in shape, with a bond angle 135 degree, bond length 121 picometer, NN bond length 175 picometer, 2 resonating structures, and also you can think about how many lone pairs are present. Easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? 4 oxygen into 2, 8 pairs, 2 nitrogen into 1, 8 plus 2, 10. That's enough. That's enough. Unless otherwise there is no permanent formal charge adopted for any atoms. Okay. Next, N2O5. N2O5 has a speciality I don't have to tell you. It carry NON bridging. There is NON bridging quite naturally. There will be 2 kind of bond length. This NO bond length is 119 picometer with 134 degree. This bond length is 151 picometer with 112 degree. So bond angle decreases, bond length increases. So here 151, here it is 119, 120 range. That is also planar in shape, and it is carrying NON linkage, NON bridging present in this molecule. That is yet another speciality of this. How many oxygen? 5 oxygen into 2, 10 electron pair, 2 nitrogen into 1, so 12 electron pairs will be there. You can take an account, you see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 lone pairs. Very simple. Nitrogen, 2 electron pairs, oxygen, 5 oxygen into 2, 10 plus 2, 12 electron pairs will be there. It's as simple as that. That is about a talk on oxides of nitrogen. Table 7.3, 7.4, very, very, very important. Okay. Now, it's about the next topic, oxo acids of phosphorus, nitric acid. It's specifically on nitric acid, not phosphorus, but nitrogen. Oxo acids of nitrogen, particularly nitric acid. Nitrogen forms oxo acids, hyponitrous acid. There is hyponitrous acid. There is nitrous acid, HNO2. And there is nitric acid. Most important one is the so-called aqua fortis. Nitric acid carries such a name, aqua fortis, meaning strong water. Nitric acid. Nitric acid is the most important one among the oxo acids of nitrogen. So it's a talk on nitric acid. It is prepared by heating KNO3 or NeNO3 with the concentrated sulfuric acid. So sulfuric acid is able to replace the volatile nitric acid from its salt solution. As that's a special property of sulfuric acid also. Sulfuric acid is oily type acid and it is less volatile. Low volatile sulfuric acid is able to replace or displace volatile acids like hydrochloric acid, HF, HNO3, etc. from their salt solution. That itself is an important property of sulfuric acid. Sulfuric acid is able to displace volatile nitric acid. Or on a large scale, it is prepared by Ostwald process. Preparation of nitric acid by Ostwald process on a large scale. What we do is, it is first one oxidation of ammonia. Ammonia oxidized with a special catalyst, platinum, rhodium, under 500 Kelvin temperature and 9 bar pressure, you are getting NO gas. And we know NO can be easily converted to NO2. And this NO2 absorbed in water, you get nitric acid. So ammonia catalytically oxidized to NO. NO very easily converted to NO2. NO2 absorbed in water, you get nitric acid. That is the commercial preparation of nitric acid, Ostwald process. Probably the major functioning or major application or usage of ammonia is also preparation of nitric acid. Okay. And there will be some NO will be extra formed, additional, not been absorbed properly. It is recycled and the aqueous HNO3 concentrated up to 68% by mass. A further concentration up to 98% achieved by dehydration using concentrated sulfuric acid. That is Ostwald process preparation of nitric acid. Next is important one, properties of nitric acid. Properties of nitric acid. It is a colorless liquid. Nitric acid is a colorless liquid. This is the dimensional parameters of nitric acid. This is a planar molecule with sp2 hybridization. OH bond length 96 picometer. NO bond length here 141 range, here 121 range. Once again, there are two different type of oxygen present in nitric acid molecule. Nitrogen oxygen bond. Nitrogen oxygen bond, here it is 121 bond angle 130 degree. Here it is 102 degree and 141 picometer. Planar molecule sp2 hybridized. Strong acid. It is a colorless liquid, freezing point 230 range, boiling point 355, much lower than water. Lower than water. Laboratory grade acid contains 68% of nitric acid by mass, having a specific gravity 1.5. It is a planar molecule with the sp2 hybridization in the gaseous state. While in aqueous solution, it is a strong acid. In aqueous solution, it acts as a strong acid, giving hydronium ion and nitrate ion. Something special regarding nitric acid is its oxidizing property. It is a strong oxidizing agent. Nitric acid is a strong oxidizing agent, attacking most of the metals except noble metals. Most metals except noble metals, gold, platinum, etc. It is attacking most of the metals and it acts as a very good oxidizing agent. As we know, nitric acid, nitrogen is in the highest oxidation state. So obviously it will be acting as an oxidizing agent. And nitric acid is a very good oxidizing agent according to its potential also. And products of oxidation, that's a very important point. The products of oxidation depends upon concentration of the acid, temperature, and nature of the material undergoing oxidation. So you get different products according to the reacting condition. according to the concentration of nitric acid, whether it is dilute nitric acid, concentrated nitric acid, very dilute nitric acid, you get different products. Whether it is low temperature, high temperature, you get different product. Whether it is zinc or copper, you get different product. So according to different material, different temperature, different concentration, you get different products. A few example quoted in the textbook you need to know, like metallic copper with dilute nitric acid. You get copper nitrate, NO and water. While the same copper with the concentrated nitric acid, you get copper nitrate, NO2 and water. So there are common factors, copper nitrate and water. So cupric nitrate and water is a common factor. With the dilute nitric acid, you get NO. While with the concentrated nitric acid, you get NO2. So that point of difference alone, if you try to memorize, no, it will be very easy, as it is a very important reaction. Okay, you see what is happening with the zinc. With the zinc, again, dilute nitric acid, you are getting zinc nitrate, water and a nitrous oxide. So the difference is over here. So cupric nitrate, zinc nitrate, water, water. Here you get NO, here you get N2O. While the same zinc with the concentrated nitric acid, these two reactions are quite same. You get a zinc nitrate, water and NO2. So these two reactions are quite the same. So if you memorize copper reaction with the concentrated nitric acid, automatically you are memorizing zinc reaction with the concentrated nitric acid. Both are giving NO2 gas. While the point of difference, memorize separately. So whichever point you can take as a common factor, try to make this. See, all these points why I am telling, because many children used to keep on continuously ask questions, sir, how to learn P block, how to learn P block. The problem arises because you consider P block as a very big chapter. Yes, of course, it is a very big chapter. Rather, I would suggest you break that chapter into simple portions. Why don't you make a nitric acid as a small chapter and learn that alone? Take down all the important points, review that points continuously, periodically. There is absolutely no point like if you go through 10 times, you are not been able to memorize. Definitely you can. It all matters how you link your memorizing ability onto each and every facts and figures. Of course, inorganic chemistry is memorizing chemistry. More you memorize, more your chances are. Right? So split the topic into small units. Take nitrogen oxide as a very small chapter, only 2 tables. Take nitric acid as a very small chapter, 1.5 page or 1 page. Over. So prepare short notes on these small chapters, study separately and review periodically. You will be able to memorize absolutely no problem. At the same time, there are several reactions. See, overall, when you look at, there are say 50, 60, 100 reactions are there. No. Many reactions you can correlate and club each other and try to make it into a common platform. Think about like that. And only the point of difference you try to point it and study separately. It will be quite interesting to memorize. Actually, we are underestimating our memory capabilities. That is the point. Now, some metals like chromium, aluminium, beryllium, etc. do not dissolve in concentrated nitric acid. Do not dissolve in concentrated nitric acid because the formation of passive film of oxide on the surface. They are made passive with the concentrated nitric acid. Aluminium made passive with the concentrated nitric acid. As it is interacting with the concentrated nitric acid, a thin film of oxide layer is formed on the surface. And that prevents subsequent oxidation, subsequent reaction. That's how aluminium made passive. Okay. Concentrated nitric acid also oxidizes non-metals also. It oxidizes non-metals also. Look at the reaction, how it oxidizes non-metals. It is oxidizing iodine to iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid, phosphorus to phosphoric acid, like that. And itself it is reduced to, see, iodine 0 oxidized to +5, nitric acid +5 reduced to NO2 +4. So nitric acid itself reduced to +4 state, iodine oxidized to iodic acid 0 to +5, carbon oxidized to carbon dioxide 0 to +4, sulfur oxidized to sulfuric acid 0 to +6, and phosphorus oxidized to phosphoric acid 0 to +5, like that, like that. And once there was a question like this, quite interesting. They are giving you 4 choices and asking you which of the following, when reacting with the concentrated nitric acid, you get 2 different gases. Choice A, B, C, D. Which, when treated with the concentrated nitric acid, you get 2 different gases. That is a question. And the answer was carbon. Answer was carbon. Hope you understand. Carbon, when treated with the nitric acid, you are getting carbon dioxide and NO2, 2 different gases. Like that also they ask. So whatever the point you feel like interesting or it can be coming as a question, you need to point it out and make a brief note and study. That's it. Okay. Next is brown ring test. Next is brown ring test. Brown ring test, all of you know, it is a test for nitrate. Test for nitrate. Nitrate are tested by brown ring test. So you take a nitrate solution, treat it with the freshly prepared ferrous sulfate. So take a nitrate solution given in the test tube. You are adding some freshly prepared ferrous sulfate, and through the walls of the test tube, we are adding concentrated sulfuric acid, where you will be get a brown colored complex forming. That is brown ring test, giving the indication of test for nitrates. So what are the reactions? What are the reactions? Reactions are nothing but basically there is a redox reaction plus a complex formation. NO3 minus, that is nitrogen plus 5, is reduced to NO plus 2, while ferrous is oxidized to ferric. Now that interact with the further, this NO interact with the further ferrous, forming a complex. What complex? FeH2O 5 times NO2 plus. What is the oxidation state of iron in brown ring complex? Old question. What is the oxidation state of iron in brown ring complex? You see, water is neutral, this is neutral, so iron is 2 plus. But the point is, even though this is neutral, in the complex, this is donating an electron to this and turn +1. And therefore, this is not 2 plus, this is rather +1. So, oxidation state of iron in brown ring complex is +1 due to ligand metal electron transition. The neutral nitrosyl donate an electron to Fe2 plus, and Fe2 plus turn Fe +1. And that actually is the reason for coloration. Right? So such points also may be asked. And of course, uses of nitric acid, the last point in that area. Uses of nitric acid in the manufacturing of ammonium nitrate, various fertilizers, explosives and pyrotechnics. Preparation of nitroglycerin. This is nitroglycerin. Trinitroglycerin. CH2NO2. Sorry. CH2ONO2. CH2ONO2. This is trinitroglycerin. Trinitroglycerin, simply called nitroglycerin. The chemical which is absorbed in Kiesel gur or the clay type material and made it controlled explosive dynamite. Dynamite make use of TNG. This is called a TNG, trinitroglycerin, TNG. Trinitrotoluene, TNT, very popular chemical, TNT, trinitrotoluene. All of you know this is toluene and this is trinitrotoluene. Trinitrotoluene, TNT, and other organic nitro compounds. Pickling of stainless steel, a surface cleaning process during the preparation of stainless steel. Pickling using nitric acid, and various such uses are commented, and that is about nitric acid, right? So the major discussion was regarding oxides of nitrogen and nitric acid. Now on to allotropic forms of phosphorus. Now on to allotropic forms of phosphorus. That is the next topic. See, there are mainly three important allotropic forms: white phosphorus, red phosphorus, black phosphorus. White phosphorus, red phosphorus, black phosphorus. And white phosphorus, it is a translucent white waxy solid. It is a translucent solid, waxy type, right? It is poisonous in nature, insoluble in water, but it is soluble in carbon disulfide. It shows the property chemiluminescence. Undergoing oxidation, burning, etc. It can show chemiluminescence. What is chemiluminescence? Giving a glow in the darkness, right? Cold light. Basically, you know, the name of phosphorus itself derived from that light carrying element. That is phosphorus. Phosphorus is well known for chemiluminescence, right? Like what you find bioluminescence in certain species, for example, fireflies. That is a bioluminescence, that is by the oxidation of certain proteins. Here, phosphorus undergone oxidation, able to show a glow in darkness, that is called a chemiluminescence, and that is a property given by white phosphorus. The reaction of white phosphorus with NaOH, that is a very popular reaction. It's a redox reaction. All of you easily understand. This is a disproportionation reaction. This is a disproportionation reaction. Phosphorus 0 reduced to -3 and oxidized to +1. A very popular disproportionation reaction shown by white phosphorus. White phosphorus react with alkali, giving phosphine, reduced to phosphine and oxidized to sodium hypophosphite, right? That is about white phosphorus, which is less stable. White phosphorus is less stable and more reactive. It is less stable and more reactive than the other solid phases under normal condition because of angular strain. It carry an angular strain. Look at the structure of white phosphorus. 4 phosphorus atoms available in the vertex of a tetrahedron. 4 phosphorus atoms available in the vertex of a tetrahedron. There is PPP connectivity. How many PP connectivity? 1, 2, 3, 4, 5, 6 PP bonds are present. 6 PP bonds are present. And the PPP bond angle being 60 degree. Due to that lower 60 degree bond angle, there is a great strain and the molecule is highly reactive hence. So white phosphorus is the least stable allotropic forms of phosphorus and is highly reactive due to that. And each phosphorus will carry a lone pair of electron. And PPP, how many PPP 60 degree you find? How many PPP 60 degree? It will be how much? Each phosphorus will make 360 degree. One over here, and one over. This is 1 and this is 2, this is 3. Each phosphorus will make 360 degree PPP angle. So there are 4 phosphorus. There will be 12 PPP 60 degree angles. Okay. So number of PP bonds, number of PPP bond angle, lone pairs, everything matters when you go through the structural entity like that. Okay. It readily catches fire to give dense white fumes. That is what involved in smoke screen reaction. Smoke screen reaction. While white phosphorus, powder of white phosphorus reacting in moisture can create thick white fumes of phosphorus pentoxide P4O10, and that will form a vortex ring. It will act like a vortex ring. It is giving like a vortex ring like this, and it creates a smoke screen. And in case of an emergency situation, if you want to escape in the war front and all, you can make use of that smoke screen, creating smoke screen using white phosphorus. That's a very important point. Okay. Next one is red phosphorus. Red phosphorus, another allotropic form of white phosphorus, obtained by heating white phosphorus at 573 Kelvin in an inert atmosphere for several days. When red phosphorus heated under high pressure, a series of black phosphorus is obtained. Black phosphorus will be some sheet-like structure, while red phosphorus is linear polymeric structure. Red phosphorus possesses iron-gray luster. It is odorless, non-poisonous. White phosphorus is poisonous, while red phosphorus is non-poisonous, and insoluble in water as well as carbon disulfide. Chemically much less reactive than white phosphorus, and it does not have the property chemiluminescence. White phosphorus having chemiluminescence property, while red phosphorus not having chemiluminescence property, right? And is not poisonous also. That is about red phosphorus. While and this is the structural entity of red phosphorus. This is how red phosphorus is available. The tetrahedral units are connected one to one like that, forming a polymeric chain type structure, while black phosphorus is somewhat sheet-like structure. Black phosphorus, somewhat sheet-like structure, that is black phosphorus. Red phosphorus is polymeric in nature, while black phosphorus we have two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus formed when red phosphorus heated in a sealed tube at 803 Kelvin. It can be sublimed in air. That means it is somewhat volatile in nature, volatile solid, and has opaque monoclinic structure or rhombohedral crystals. It forms monoclinic or rhombohedral structure, which we are learning in solid state chemistry, and the molecular dimensions many of you may be remembering. It is not oxidized in air. Beta black phosphorus prepared by heating white phosphorus at 473 Kelvin under high pressure. It does not burn in air up to 673 Kelvin. That's about the important allotropic forms of phosphorus. White phosphorus, red phosphorus, black phosphorus. White phosphorus most reactive than red phosphorus than black phosphorus. Black phosphorus is most stable than red phosphorus than white phosphorus. Okay. Next is a talk on very important compound of phosphorus, phosphine. A very important compound of phosphorus, phosphine. Phosphine, prepared by reaction of calcium phosphide with water or acid. Calcium phosphide reacting with water or acid, you will get phosphine gas produced. Calcium phosphide is phosphorus 3 minus state. Phosphine is phosphorus 3 minus state. Same thing. There is no change in the oxidation state, as it is a hydrolysis reaction. Or in the laboratory, you see the importance of the reaction. Just now we have seen the same reaction. White phosphorus undergo disproportionation. You get a phosphine as a important compound obtained in that reaction. White phosphorus undergoing reduction, you get phosphine. Oxidation, you get sodium hydrogen phosphate. Again, the same reaction repeating. When pure, it is non-inflammable, but becomes inflammable due to the presence of either diphosphine or phosphorus vapors. mostly phosphine will be contaminated with phosphorus vapors. And that actually is involved in smoke screen earlier I was talking about. So the presence of diphosphine or phosphorus vapors make it inflammable. To purify it from impurities, it is absorbed in HI to form phosphonium iodide, which on treating with the KOH, you get pure phosphine. So pure phosphine can be obtained. Impure phosphine treated with the HI, you get phosphonium iodide, which you can separate out, and that when digested with alkali, you will get a pure phosphine. That is about phosphine, PH3. And coming to the properties of phosphine, as all of you know, it is a colorless gas with a rotten fish smell. It has got some foul smelling character. It has got rotten fish smelling character, foul smelling character, and is highly poisonous. It is highly poisonous. PH3 is highly poisonous. Right? It explodes in contact with the traces of oxidizing agent like HNO3, chlorine, bromine vapors, etc. Right? So, phosphine is a very good reducing agent, even better reducing agent than ammonia. Phosphine is a good reducing agent, better reducing agent than ammonia. Down the group, for hydrates of nitrogen family, down the group, the reducing property increases. So phosphine is a better reducing agent, and being a good reducing agent, interact with the strong oxidizing agents. Nitric acid is a good oxidizing agent. Chlorine is a good oxidizing agent. Bromine is a good oxidizing agent. There will be explosive type of reaction given between them. Right? It is slightly soluble in water. Solution of PH3 in water decomposes in presence of light, giving red phosphorus and hydrogen. When absorbed in copper sulfate or mercury chloride, with the copper sulfate or mercury chloride, you will be getting corresponding phosphide. Copper phosphide will be obtained, mercuric phosphide will be obtained. Phosphine is weakly basic. Phosphine is weakly basic. Which is more basic, ammonia or phosphine? Which is more basic? Down the group, for nitrogen family hydrides, down the group, basic character decreases. Basic character decreases. Ammonia is better basic than phosphine. So phosphine is weakly basic. Ammonia is also weakly basic, but phosphine is again weaker compared to ammonia. Gives phosphonium compound with the acid, PH3 with HBr giving PH4Br. If you go through the uses, you can find a talk on Holmes signal. Holmes signal. What is Holmes signal? In steel containers, in warship and all, there will be steel containers filled with calcium phosphide and calcium carbide. There will be steel cylinders containing calcium phosphide. In a steel cylinder, there will be calcium phosphide and calcium carbide. And the cap of the cylinder is opened and thrown to seawater in case of an emergency. So in case of an emergency, the cap is opened and thrown to the water. Water will enter into the system. Water will enter into the system and it will undergo hydrolysis. Calcium phosphide upon hydrolysis, you get calcium hydroxide liberating phosphine gas. Calcium carbide upon hydrolysis, you get calcium hydroxide and acetylene gas. Acetylene gas will immediately catch fire. Acetylene gas will immediately catch fire, and in that fire phosphine will burn. Phosphine will burn, and that burns with a, actually phosphine with the impurities catches fire, and in that fire acetylene burns with a brilliant light. Hope you know the burning of acetylene. Burning of acetylene gives a brilliant light, right? So just now we have seen phosphine always contaminated with the diphosphine or phosphorus vapors, it will catch fire. In that fire, acetylene gas will burn with a brilliant light which is visible from long distance, can act as a signal, that is Ohm's signal. That is commented there somewhere in the, yes, it is given here. Containers containing calcium carbide and calcium phosphide are pierced and thrown in the sea where gases evolved to burn and serve as a signal. It is also used in smoke screen. Smoke screen just now discussed. The phosphorus vapors or phosphine, when it is burning, you may get a P4O10 phosphorus pentoxide. Formation of phosphorus pentoxide forms a vortex rings, create as a smoke screen, right? And that is about phosphine. There is an important question. Bond angle in pH4 higher than in pH3. Why? Bond angle in pH4 plus higher than pH3. Very simple logic. pH3 is somewhat pyramidal in shape, almost 90 degree. We can say sp3 hybridization, trigonal pyramidal geometry. Bond angle is less than 100. Ammonia bond angle is 107.8 degree, while phosphine is less than 100. And as you come down, the relevance of hybridization is almost negligible and is coming close to 90 degree combination of pure p orbitals. That is what happening. Anyway, phosphine, if there is a question what is hybridization, we can say it is sp3, and rather it is basically coming close to the pure orbital combination 90 degree bond angle, while close to less than 100, while pH4 plus is purely tetrahedral geometry. It is a regular geometry, tetrahedral geometry. This is pH4 plus, and that will maintain tetrahedral is usual regular geometry. 109 degree 28 minutes, 109.5 degree bond angle will be maintained in pH4 plus, as there is lack of that lone pair. No lone pair is present that is utilized to link with the H plus, right? So this bond angle will be 109.5 degree range, and this bond angle, as all of us know, it is below 100 compared to ammonia. As you come down the group, bond angle decreases and coming close to 90 degree, that identical with the pure p orbitals. That is about phosphine. Next is phosphorus halides. Learning phosphorus halides, you can learn phosphorus trichloride, phosphorus pentachloride as a combination. That will be a better idea to learn PCl3, PCl5. Mainly we have two types of halides, PX3. It can be PF3, PCl3, PBr3, PI3, and PF5. Very important to note that there is no iodide. PI5 not available. It can be PF3, PCl3, PBr3, PI3. It can be PF5, PCl5, PBr5, not PI5. Phosphorus is not forming PI5. Right? Thermodynamically, it may not be favorable because Pi bond strength is a matter of point. Iodine is large atom, 5 large iodine atoms surrounding, that is not also favorable. So thermodynamic and various reasons does not favorably help the formation of Pi5. That is a point. Anyway, so talk on PCl3 and PCl5. It should be studied parallelly. Look at PCl3 reaction. First of all, PCl3. This is the structural entity of PCl3. sp3 hybridization, trigonal pyramidal geometry with one lone pair and 3 bond pairs. That is PCl3. It is obtained by reacting white phosphorus with the 6 chlorine. You get PCl3. White phosphorus with the 6 chlorine, you get PCl3. While white phosphorus with 10 chlorine, you will get PCl5. So it is a comparative study, I would say. You see, P4 with 6 Cl2 4 PCl3, P4 with the 10 Cl2, 4 PCl5. So it should be studied comparatively. Now again, white phosphorus with the thionyl chloride, you get PCl3. While white phosphorus with the sulfuryl chloride, we get PCl5. SOCl2, thionyl chloride, P4 with SOCl2, you get PCl3, SO2, S2Cl2. Slight change. White phosphorus with SO2Cl2. What is SO2Cl2? SOCl2 is thionyl chloride. SO2Cl2 is sulfuryl chloride. With the sulfuryl chloride, we get PCl5 and SO2. Slight difference, but identical reaction. Now PCl3, it is colorless, oily liquid. PCl3 is colorless, oily liquid. What about PCl5? It is greenish white powder. PCl5 is greenish white powder. PCl3 is colorless, oily liquid. In the presence of moisture, it is hydrolyzing. PCl3 hydrolysis, you see PCl3 hydrolysis, PCl3, 3 water molecule, you get S3PO3 HCl. S3PO3 HCl. Here phosphorus is plus 3 state. Here phosphorus is plus 3 state. During hydrolysis, almost the oxidation number will remain the same. That is about PCl3. What about PCl5? Look at PCl5. How PCl5 hydrolyzes? Of course, PCl5 undergoing hydrolysis, you get H3PO4 plus 5 state, plus 5 state. But that happens in 2 steps. I mean, that can be illustrated by 2-step operation. There it is a single mode of reaction. White for PCl3 react with the water, you get S3PO3, 3HCl. Single mode of reaction, 3-step operation. While here, it is 2-mode operation. Here, PCl5 with water, you are getting POCl3, removal of 2 chlorine, 2-step operation here, and then 3-step operation here. Here it is, one type of reaction, 3-step operation, 3 times HCl out, like that. Here it is 2-step reaction first, then 3-step reaction. That means 2 mode of reaction. In the first mode of operation, you are getting POCl3 phosphorus oxychloride, and in the second step of reaction, you are getting S3PO4. Very important point. The point of difference all of you may be aware of. Why such a difference? In PCl3, all the 3 chlorine phosphorus chlorine bonds are identical, whereas in PCl5, it is not so. This is PCl5, 3 planar bonds and 2 axial bonds. Axial bonds are more elongated. Here, all the 3 chlorine are identical, and there is identical hydrolysis of the 3 chlorine atoms, and there it is. Chlorine replaced by OH, and finally you are getting S3PO3 phosphorus acid. While here, the 2 chlorine atom in the axial position, which are more elongated and relatively weak bond, will be hydrolyzed first, and then you will be getting POCl3. This 2 chlorine gone, and you will get POCl3 first, and POCl3 will be like this. This is POCl3, phosphorus oxychloride. And now these 3 chlorine atoms are replaced subsequently by hydrolysis, finally getting H3PO4, like that. So in PCl5, there are non-equivalent bonds. 2 axial bonds are more elongated, slightly weaker compared to 3 planar bonds. That is the reason why the hydrolysis occurs in 2 different steps. So that type of comparison and relative study is needed when you handle PCl3, PCl5. That is about the reactions and properties of PCl3, PCl5. Furthermore, about PCl5, this is the decomposition of PCl5. All of you know, PCl5 decomposes giving PCl3 and Cl2. And the reason is, once again, the same. The axial bonds are more elongated than planar bonds. Axial bonds are more elongated than planar bonds. Even it is interacting with the alcohols and the carboxylic acid, replacing that OH group. The OH group of alcohol, the OH group of carboxylic acid can be replaced by PCl5. You get this OH group replaced by chlorine, ethanol giving ethyl chloride. This OH group is replaced by chlorine, ethanoic acid giving ethanoyl chloride, like that. Even it can react with the finely divided metals. With the finely divided metals, it can react, forming metal chlorides and PCl3. And this is the structural entity of PCl5. All of you know, this is the structural entity of PCl5. It is maintaining sp3 hybridization, sp3 hybridization, and the molecule is AB5 type. There are 3 planar bonds, bond length 204 picometer, and 2 axial bonds, bond length 240 picometer. Axial bonds are more elongated than planar bonds. What is the reason? Why the axial bonds are more elongated than planar bonds? Very simple. See, planar bond angle, this bond angle is 120 degree, while axial bond angle is 90 degree. Lower the bond angle, greater will be the bond length. When the bond angle decreases, bond length has to be compensated in order to maintain the minimum repulsion. So to maintain minimum repulsion, when the bond angle is lower, bond length should be compensated. Bond length will be increasing. So axial bonds are more elongated compared to planar bond. Planar bond is 120 degree, axial bond is 90 degree. Clear? So how many 120 degrees present in PCl5? How many 120 degrees? In the plane. 3 120 degree. How many 90 degree present? How many 90 degree present? There are 6 90 degrees. One here, one here, one here. 3 on top, 3 at the bottom. There will be 6 90 degree angle in PCl5 and 180 degree. This will make 180 degree bond angle. So there is 180 degree, 3 120 degree, and 6 90 degree bond angle in PCl5. And that is the scenario of PCl5 in the gaseous state. While it is moving to solid state, in the solid state, it is available as ionic solid. PCl5 in the solid state. PCl5 in the solid state exists as ionic form. PCl4 plus, PCl6 minus. PCl4 plus will be like this, tetrahedral. PCl4 plus, sp3 hybridization tetrahedral. While PCl6 minus, it is sp3d2 hybridization and is octahedral. This is PCl6 minus. So PCl4 plus tetrahedral, sp3 hybridization, PCl6 minus, sp3d2 hybridization, octahedral geometry. That is about PCl3 and PCl5. 2 important compounds of phosphorus. So, allotropic forms of phosphorus, phosphine, PCl3 and PCl5, right? Next, it is about oxo acids of phosphorus, various oxo acids of phosphorus. That's a very important topic from the concerned chapter, oxo acids of phosphorus. Let us see various oxo acids of phosphorus. Let's see one by one. First one, hypophosphorus acid. Hypophosphorus acid, also called a phosphinic acid. Hypophosphorus acid, also called a phosphinic acid. H3PO2 plus 1 state obtained by reacting white phosphorus with the alkali. white phosphorus with alkali. Basically, we are getting the salt. H3PO2. 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 See, learning the structure of these acids are very important. I would say you should not by heart the structure. I would say you must use your logic to learn the structural entity character. Please try to understand. Normally they will make a tetrahedral arrangement. So you can write phosphorus 1, 2, 3, 4 like that. Okay. Now there will be minimum one PO double bond. There will be minimum one PO double bond. And there will be minimum one POH bond. That is an essential bonding present. So tetrahedral geometry, number 1, PO double bond, number 1, number 2, POH bond, number 3. This is essential. The rest you can do according to the formula. You see that H3PO2, 2 oxygen over 2 more hydrogen available. So it will be 2 hydrogen like this. This is the structure of H3PO2, that is hypophosphorus acid, popular known as phosphinic acid. Phosphinic acid. And very well you can understand, it is a monobasic acid. This is the one and only hydrogen which can ionize. So this is the one acidic hydrogen. That is the one acidic hydrogen. So there is only one acidic hydrogen, hence it is monobasic in nature. Monobasic in nature. While these two hydrogen are reducing hydrogen. These two are reducing hydrogen. They are not connected to oxygen. They are connected to less electronegative phosphorus. They are not ionizable hydrogen. They are not labile hydrogen. They are not acidic hydrogen. Rather, they are reducing hydrogen. Quite not surprisingly, hypophosphorus acid is one of the best reducing acid from oxo acids of phosphorus. Among the oxo acid of phosphorus, hypophosphorus acid is the good reducing one. There are 2 reducing hydrogen, right? Obtained by the action of white phosphorus with the alkali. It is +1 oxidation state. How come +1 oxidation state? How come +1? -2, +2, -1, +1, +1, -1, +1, -1. You get +1 oxidation state, +2, +1, +3 and -2, +1 state. Next is orthophosphorus acid, also called a phosphonic acid, H3PO3, H3PO3. And this is H3PO3, H3PO3. Once again, you can put like this 1, 2, 3, 4 tetrahedral geometry. 1 PO double bond, 1 POH bond. What remaining? There are more hydrogen, 1 more oxygen. So I am giving 1 more OH. So oxygen is over, 1 more hydrogen like this. So there is 1 reducing hydrogen and it is a dibasic acid. It is a dibasic acid. Right? So the oxidation state will be -2, +2, -1, +1, -1, +1, +1, -1. You will get +3 oxidation state. And it is a dibasic character and there is 1 reducing hydrogen. There is 1 reducing hydrogen and it is a dibasic acid character. Right? There is a question, which is more acidic? Which is more acidic? Hypophosphorus or phosphorus? They are almost equal, but when you look at meticulously, you can see hypophosphorus. This is better acid than this. When you look at the Ka data and all, even though marginally, this is slightly more acidic than this. Because the acidic character can be, many times, acidic character can be explained by the number of PO bond, number of double bond oxygen versus number of OH group. Here, 1 OH group, 1 double bond O. Here, 2 OH group, 1 double bond O. So, number of double bond O per OH group is less here. Number of double bond O per OH group can decide the acidic strength. So here one double bond of one OH. Here one double bond of two OH. So per OH will be half only. So the number of double bond of per OH group can decide acidic strength. So when you look at it in that sense, this is slightly more acidic than this, right? And that is obtained by reacting P2O3 with water. P2O3 is anhydride of phosphorus acid. Okay. Next is pyrophosphorus acid, H4P2O5. How can we get the structure? H4P2O5. 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 Pyrophosphorus acid. Very simple. You try like this. Phosphorus. 1, 2, 3, 4. 1, 2, 3, 4 like that. 1 PO double bond. OH group. That is essential. Now there are hydrogen, 1 oxygen. So you can give 1 oxygen here and 2 hydrogen here. Now it is H4P2O5. H4P2O5. Right? The third compound, pyrophosphorus acid, H4P2O5, and is again, what is the oxidation state? You can find out, no? Oxidation state -2, -1, -1. So -2 + 2, -1 + 1, -1 + 1 + 1 -1. So it will be +3 state, +3 state, +3 oxidation state, which is obtained by action of PCl3 with H3PO3. PCl3 with H3PO3. Right? So by hearting the structure, I would say you don't by heart, rather apply some logic for drawing the structure. Give phosphorus, give tetrahedral, give 1 PO double bond, give 1 POH, give the rest according to the formula. Okay. Next it is hypophosphoric acid, H4P2O6, hypophosphoric acid, H4P2O6. How can you draw? H4P2O6. What can be done? Phosphorus, 1, 2, 3, 4, 1, 2, 3, 4 like this. PO double bond, OH group. Sufficient oxygen present. So I am giving one more OH group. Now hydrogen over, oxygen over, everything over, one bond is remaining there. So what I am doing is just connect it to the 2 phosphorus. PP bond will be present and is tetrabasic in nature. It is tetrabasic in nature. Is it clear? Tetrabasic character, 1 PP bond, PO double bond, like that. Right? That is hypophosphoric acid. There is 1 PP bond. Red phosphorus with alkali, you get that. White phosphorus with alkali, you get this. Red phosphorus with alkali, you get this. So you can correlate like that also. Even you can correlate. So these two reactions, you can correlate. Like that. There are similarities. Next one, orthophosphoric acid, H3PO4. Orthophosphoric acid, H3PO4. H3PO4. So you have phosphorus 1, 2, 3, 4. There is PO double bond, there is OH group. Sufficient hydrogen, sufficient oxygen. Therefore, one more OH. Again oxygen available, again hydrogen available. One more OH. It is a tribasic acid. And here even you can have a look at 1 double bond O per 3 OH group. So for 3 OH group, 1 P double bond O. That makes it is slightly lower acidic character compared to phosphorus acid. So hypophosphorus acid relatively better acidic than phosphorus acid, than phosphoric acid. This is phosphoric acid, orthophosphoric acid. tribasic acid character. And it will be, what is the oxidation number coming? What is the oxidation number coming? -2, -3, -4, -5. It will be +5 state, +5 state. So I never advise learning the structures by heart. Rather, I would say you apply the logic to draw the structure simply looking at the formula. Next is H4P2O7, pyrophosphoric acid. H4P2O7, pyrophosphoric acid. Have a look at pyrophosphoric acid. H4P2O7, phosphorus like this. It is PO double bond, OH, OH, H4P2O7. So once again OH, OH, and one O here. H4P2O7, everything is over. There is one POP linkage. There is one POP linkage. There are 4 OH group, tetra basic character. Right? And the last one, metaphosphoric acid. Metaphosphoric acid. Metaphosphoric acid, actually there is a open chain structure and cyclic structure also. There is cyclo-trimetaphosphoric acid and open chain linear structure also available. Metaphosphoric acid. How to draw the metaphosphoric acid? Open chain structure. HPO3 n times. HPO3 n times. It will be like this. Phosphorus 1, 2, 3, 4. Right? Phosphorus 1, 2, 3. Phosphorus 1, 2, 3. Phosphorus 1, 2, 3. You can go like this. It's a linear polymer structure. There will be one PO bond, one POH bond, one POH bond, one PO bond, one PO bond, one POH bond, one PO bond, and one POH bond. It will continue like that. That is linear polymeric form of polymetaphosphoric acid. Polymetaphosphoric acid. It is available in the cyclic form, cyclo-trimetaphosphoric acid. And there are various varieties. Various varieties are there. Cyclo-trimetaphosphoric acid 3 times. HPO3 3 times. You can do it like this. Phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen like this. Now give the essential bonding. P double bond O and POH. P double bond O and POH. P double bond O, POH like this. This is cyclo-trimetaphosphoric acid. There is hexametaphosphoric acid. And the sodium salt of hexametaphosphoric acid we are using in the removal of hardness, polymetaphosphoric acid, Calgon process. So that is about the various oxo acids of sulfur, drawing the structure and knowing the basicity, knowing the oxidation state, preparation method, everything you need to review, particularly the name, formula, name including common name, name including common name. Okay. And already commented, it is a reducing character. pH bond is reducing in nature. Look at the disproportionation of H3PO3. Look at the disproportionation of H3PO3. H3PO3 phosphorus plus 3 is oxidized to +5 and reduced to -3. Oxidized to +5 and reduced to -3. The pH bond are reducing in nature, and H3PO2 contain 2 pH bonds, already commented. This is H3PO2. There are 2 reducing hydrogen. There are 2 reducing hydrogen. And that can react with the silver nitrate. Ag plus will be reduced to Ag. and itself it is oxidized to phosphoric acid. That is why phosphinic acid is a good reducing acid from oxo acid of phosphorus. And there we conclude the oxo acid of phosphorus, the very important topic from that chapter, right? And the next is group 16. So far it was group 15. What we have discussed is the fundamental idea starting, that is the general properties and all. We had a specific talk on hydrides. Hydrides was specifically discussed for all the families, right? Then there was a talk on dinitrogen, ammonia, oxides of nitrogen, right? Then nitric acid, there was a talk on nitric acid, allotropic forms of phosphorus, phosphine, PCl3, PCl5, and most importantly, oxo acids of phosphorus. Next is group 16, oxygen family. Group 16, that is oxygen family.